Okay, well, let's start with some stories. Why on earth are you here? What are the skills that you're going to get, and how can you apply them to actual core projects? But before we get into the stories, you probably just need a little bit of background about what does this tool do? And so most of you are familiar with things that look like this, right? This is 1D hydraulics in RAS. In RAS, we conceptualize the world as a series of cross sections. And the water, what color is water in RAS? It's blue. How often is water blue? Never. And so I like to call this blue water modeling, and that's a little bit of a sneaky pejorative. But what this is truly called is fixed bed modeling. Now you don't call it fixed bed modeling, you just call it hydraulic modeling. But you're about to start calling it fixed bed modeling because we're going to learn the alternative, which is mobile bed modeling, which means that there used to be one surface that changed over the course of your simulations, and that's the water surface. Now there's going to be two surfaces that change. The water surface is going to change, and the bed is going to change. The cross sections used to be fixed in time. Now they're going to adjust in time. So we solve sediment flux through a control volume, and the controlled volume is your cross section. And we end up changing your cross section based on whether there's too much or too little sediment. And this is a reservoir delta. You can actually change the profile enough that it matters and has feedbacks on your hydraulics. And so that's what mobile bed modeling is. Okay, so let's tell you a few stories. These are projects I've worked on with 1D sediment modeling, and most of them are in this talk. Some of them have topics go in and out of this talk depending on my audience. But these are, you can see we're all over the United States and world. Okay, so the main takeaway is that we have used mobile bed sediment transport modeling in every one of the Corps' business lines. There is nothing that the Corps does where not every project needs a 1D sediment model. We've already kind of mentioned every project should have some morphological analysis to make sure that there isn't a problem, but not every project needs a 1D sediment model, but every business line has projects that need a sediment model. And so we're going to talk about flood damage reduction, reservoir management, dredging, and restoration, but there have been others. So first of all, let's start with flood damage reduction. So on the last episode of the podcast, I talked to Chris Nygaard, and we met back on the, what I'm just going to call the Mount St. Helens reboot. Okay, Mount St. Helens erupted before some of you were born now, but this was the morphological event of the last generation, the generation before me. Kind of anyone who was anyone in the sediment community got involved in this project because Mount St. Helens basically, it wasn't a classic eruption. The eruption followed a landslide. Basically, half the mountain flipped upside down. And we're about 3.8 billion, with a B, billion tons of fresh sediment was released into this watershed. Downstream of this event is a river that reaches a series of communities that are protected by levees. Okay, so let's use our intuition. Actually, I think this is one of the Kahoot questions. If you put hundreds of millions of tons in a river that's protected by levees, what's going to happen? It's going to deposit. You're going to lose level of protection. All right. So the first round of analysis, they built the sediment retention structure, and this is was a giant dam that held back. I think there's about 200 to 300 million tons of sediment behind it, and that intercepted a lot of the sediment load and maintained the level of protection downstream. But in the late 90s and early 2000s, the dam filled to the spillway. Now that doesn't mean the dam is full because the way that reservoirs work. If you've got a structure here, you can fill the structure with sediment to the spillway, but you've only actually filled about half the capacity of the reservoir because you're going to continue to grade all the way up until you kind of hit the grade of the valley. And so it's only about halfway full of sediment, but there's something happens when you reach the spillway is that sediment starts to pass. Your trap efficiency drops significantly, and you start passing, like 30 to 40% of the sediment downstream, and that's too much if you've got downstream levees. And so, Chris Nygaard in the Portland district, they stood up a study and looked at a bunch of wild alternatives about what we could do, and they ended up raising the spillway, but they wanted to see how much sediment could we pass downstream, and more importantly, we talked about this a little bit in the podcast, more importantly, what grain classes? And can we modify the structure to keep the grain classes that would deposit, but pass the grain classes that wouldn't? And so it's a little bit of a complicated process, and so the question is, well, what's going to deposit where, depending on how we modify this structure? And so we had a 1D hydraulic model of the reach with the levees, and we looked at a bunch of different scenarios, and they had repeated cross sections. And so John introduced you to the longitudinal cumulative volume curve. You're going to want to get used to thinking about data this way, because sediment data are too noisy to just look at how much mass change at each cross section. And so we accumulate mass change from upstream to downstream and look at kind of the trend, which means that a positive slope means deposition, and a negative slope means erosion. And the steeper that slope is, the more aggressive that is. And so here we have deposition that happened kind of after the dam filled to the spillway, and these are from repeated cross sections, and so that is the trend of actual deposition. So that's kind of a linear slope, a linear positive slope. So in a longitudinal cumulative volume curve, what does a linear positive slope mean? A relatively constant level of deposition. There isn't like a place where you have a deposited hotspot or erosion. You've got general steady deposition, and then the points are, this is our model of the system. So we're able to reproduce the deposition in the system. So then when we gained the different alternatives to the SRS, we could look at how does that decrease or increase deposition based on how much sediment we're releasing and which grain classes. Then one of the cool things you can do is, you're changing the cross sections. So what we did is we would change our alternative. We look at 50 years of sediment deposition downstream, and then you can output the final set of cross sections as just a RAS geometry and do a series of steady flows and just kind of put it in FDA and look at what is the flood risk, how does the flood risk change at the end of this 50 years, and what is the cost benefit of raising the levees or things like that. And so that's how you use mobile bed for flood risk analysis. We already talked about Euclid Creek. Euclid Creek, this is actually my first sediment model. This was before I was at HEC. I used the classic sediment transport model, HEC-6, but then it became one of my test data sets when we did this. And so we developed a 1D mobile bed model. And so you can see this is the steep hypercritical, supercritical channel. Hypercritical, that's a different thing. That's bad parenting. This is the steep supercritical channel. I like that. It's like a parenting crude number, because I think the hardest thing about parenting is when to be hard and when to be soft, and like making those decisions in real time. And then there's another human making those decisions too, and depending on whether or not you have eaten or slept well, you're making those decisions differently. I love the idea of like a parenting crude number. You want a parenting crude number of 1. Yeah. So there, that went. I'm glad we got that on the video. But you have this supercritical channel, and of course everything is always vertically exaggerated in RAS. And if you're not used to looking at RAS, just know that everything's vertically exaggerated in RAS. And then you have the tailwater of the Great Lakes, and things widen and get shallower here. It's like a perfect storm. There are three converging events that are going to give you deposition, and so we were able to simulate this, and so you can see the bed is changing in response to the deposition. And as the bed changes, now the water surface elevation changes. And so we would run 4 years of deposition, and really what we're looking at is what is the maintenance schedule going to have to be in order to maintain the benefits, and can we look at the cost benefit? Okay, so the project's a sunk cost now. The future benefits have to be compared against maintenance. And maybe we should have taken that into consideration. One of the things that happens a lot with sediment is that maintenance gets discounted. There's like a voodoo that economists do, and I I understand it, and it makes sense mathematically, but it never works out for us the way it seems it should, is that future maintenance is always discounted to the point that it doesn't matter. But empirically in the world, it does matter, and it ends up ruining some of our projects. And so there's a whole kind of realm of study. One of John's old professors, Roland Hodgkiss, is kind of examining this idea of how we economically discount future maintenance to the point that after 20 years, it doesn't affect our projects at all. And should that really be the case? But so now what we're doing is we're looking at different maintenance strategies in order to determine the cost benefit of maintenance in this channel. All right, this is probably one of my favorite studies. This is Big Rapids, Michigan. And Big Rapids, Michigan, there's a series of dams. And so this dam, if you look at this dam on the map, and I was to ask you, what is the reservoir extent of this dam? You would look at this like chubby section here and say, well, probably the reservoir is here. You know, that's the reservoir pool. But this reservoir's been in here for 100 years. And the sediment deposition from this reservoir is affecting water surfaces all the way up to here in the downstream end of the community. And you can tell from the profile, obviously, but you can also tell by the gravel-sand transition. One of the magical things that happens in gravel rivers is that gravel rivers get finer downstream. Gary Parker has a chapter in the ASC Manual of Practice 110, which is kind of the book that everyone should probably have on sediment, even though it's more than a book, it's a small library. But he did some of his early work in Japan and Canada, and one of the things he noticed is something that I noticed as I've been wading these systems is you notice that gravel systems get finer as you go downstream. It goes from cobble to gravel to, and that all happens gradually, but then all of a sudden you step and all of a sudden you're in sand. In like 20 meters, it goes from full armored gravel bed to full sand bed. And that is one of the like mysteries of the universe, and there's lots of theories on it, but you see it here in Muskegon. Right here, you transition from gravel to sand, which means you're hitting the backwater effect of the dam. And so look, that's like miles upstream. So what also affects flooding in Michigan? Ice. And so I wanted to call this paper a song of ice and sediment because after the George Martin series. So they are getting ice jam flooding, and their flood maps are completely erroneous because they're getting ice jam flooding, and their FEMA flood maps don't take into account sediment deposition or ice jam, and more importantly, the interactions. The deposition from the reservoir is actually inducing ice jams. The ice jam frequency has increased over the years. And so I paid an intern. Her summer job was to go to the Big Rapids Library, and they actually have a local newspaper that's been running for 130 years. And I put together a little hydrometeorological model and identified the 1,000 dates I thought were most likely to have ice jams. And she pulled the microfiche for all 1,000 dates and identified 12 ice jams. And so then she gave me those dates. I retrained my model and hired her the next summer to go check another 500 dates. And she found 2 ice jams early on, and then for the last 300, no more. And we felt like we got them. The reason I tell that story, well, it's idiosyncratic, and it's kind of fun. The reason I tell that story is that, I think it's really important for you to realize that not all of the evidence that you need for your studies that's available can be Googled. I think there's a sense in emerging generations in particular that if I can't Google it, it doesn't exist. And it's just not true. There's a lot of evidence that you can bring to bear on these problems that is available to you. But you have to kind of think creatively about it. And so this is what it looks like. This is the pool, and then you essentially get the reservoir deposits all the way back up here. Even though if you look at the Google map, that looks very riverine, doesn't it? That's a reservoir. From a morphological point of view, that's a reservoir. And where do ice jams form? Well, they form on changes of slope. So they usually form right where you get the flatwater pool because the ice gets thicker there. But they also form on this change of slope between the natural reach and the delta. And that's exactly where they form. Oh, we also did some dendrochronology. This is cool. Again, not all the evidence that you need is Googleable. We took tree cores because when an ice jam happens, it damages trees and leaves evidence in the trees. So I hired another graduate student who does dendrochronology, and we looked for the historic evidence of these things in the trees. We asked the trees. And so we did an ice jam in RAS. I don't know if you knew you could do that. You could do ice jam analysis in RAS. And we calibrated it to the tree scars and some survey data. But then, this is the reservoir delta. You kind of see that? Here's the actual grade of the river, and then here's the historic grade. All of this is reservoir delta. And so that's about 100 years of deposition. So I calibrated a sediment model. I built a sediment model based on what I thought the bed would look like 100 years ago. And then I calibrated the deposition, the sediment deposition over the last 100 years. And this is my calibration, the observed, or the bed change from before the dam till now, and the computed. And then we projected it 50 years into the future, so that we could see if, what is the continued deposition going to do to the future ice jam risk. And then we reran the ice jam model on top of the future deposition situation. We also did a lot of cool stuff. And so then we updated, if you get into ice jam statistics, it's a joint probability distribution. But we updated the joint probability distribution both for the ice jam, but also for the future ice jam risk based on sediment deposition. And so this is the ice-influenced, sediment-influenced future flood risk. And it's like 4 feet higher for the 1% event. And that is an actual flood risk for this community. And then we provided a number of different sediment management options that they can do. Oh, we have paper on this. Okay, so those are some samples of how we use sediment transport in flood risk management. Reservoir management is obviously one of the big uses of sediment transport. When you build a dam, we were talking the other day about how do you describe your vocation to other people. I said as little as possible, right? I have the 1 minute rule. But if someone presses, and we get to the point where it's like, there's dirt on the bottom of the river. Like, I actually study how that dirt moves. We never call it dirt in these settings, but that's the best I can do to try to get out of that conversation as quickly as possible. But if they press me, I say, okay, here's an example. You build a dam, you turn a river into a lake, and all the river dirt, because I'm still calling it river dirt at that point, all the river dirt that used to pass through there just kind of piles up. And eventually, you fill the lake. And my friend John Shelley likes to say, I actually say this if we get this far into the conversation, my friend John Shelley likes to say that all reservoirs and dams have a 100% failure probability for filling up with sediment on a long enough time scale. And usually that's enough to be impressive, and then we can talk about, their job, or the Premier League, or Kierkegaard.
Super Bowl.
The Super Bowl, yeah. If it transitions to Kierkegaard, that's a good party. But there's a couple of things that go on here. Is that yes, we do deposit upstream in the reservoir, but all of that sediment gets intercepted. And now you're already kind of building your morphological intuition, right? And so what happens to QS here?
Goes down, down.
Right? Yeah. What happens to Q?
Should be the same.
Well, total flow volume's the same.
At an equilibrium.
But the lows come up and the highs go down. But what do we know about sediment transport?
It's not linear.
It's nonlinear. So if you bring the lows up and the highs down, what happens to transportability all told?
It will be almost linear.
Goes down.
Goes down.
Because you've brought down the peaks, which are doing more of the work.
Mm-hmm.
If you kind of even out, it's the same volume, but if you even out the volume, the transportability goes down. But usually, and so you know, if we, okay, so,
But it became ferry chops now.
right, so now we've got forcings that go in both directions, right? We've decreased the transportability, but we've also, we've basically shut off the sediment load. And so usually decreasing the sediment load is more important, overwhelms decreasing the transportability just downstream of the dam. And so you get scour downstream of the dam. And this is where people like to talk about hungry water. I actually like the hungry water thing. It's evocative, right? And then, again, if that conversation goes to 8 minutes, we usually end up talking about hungry water. But that's a real that person's usually a high school science teacher at that point. But you get farther downstream, you have a tributary that's bringing in its original sediment load. Now it matters that you've decreased the transportability of this system because you'll get some deposition downstream of that tributary. And for example, on the Trinity River, if that's cobble and boulders gravel cobble and boulders that salmon spawn in, well, now you're depositing a bunch of sand on top of that, and it's a catastrophe. So there's lots of sediment complexity around dams. And so I want to introduce you to the Arghan Dab because you're gonna model the Arghan Dab tomorrow. The Arghan Dab Reservoir is one of the reservoirs in Afghanistan. And a lot of people don't know that Kandahar actually means 5 brothers. And it's from a kind of historical tale of 5 brothers who built a dam. Because dam building is so important in this region because all of the water falls as snow on the Hindu Kush Mountains. And then you have to trap it as it comes in the spring runoff in order to have any agriculture in those valleys. And so there's a series of really important reservoirs that trap that water, and they have multiple year capacity, but this is subsistence agriculture. And so if these reservoirs don't deliver the necessary water, this is kind of higher stakes than almost anything else I do in my day because people will die. Like there will be famine conditions. And the problem is that here is the watershed of the Arghan Dab Reservoir. I'm not sure there's a tree in that whole thing. And so when I first started working on this project and I looked at the sediment loads, I was like, that's not right. That's not possible. Well, it is if you're in a mountainous watershed. They call these the Badlands of Afghanistan. And so the sediment loads are immense. And so the reservoir is about 40% full of sediment. And so now let's think this through. We've got a reservoir that is delivering water to subsistence agriculture, but it's filling with sediment. What is the drought resilience of this system? How is the drought resilience of this system changing? Well, it is decreasing, right? The ability to provide water in a multi-year drought is decreasing the more storage you lose. And so we built a model of this reservoir, and this is the model that you're gonna play around with a little bit. This is obviously a Soviet dam, and the Soviets were very good at keeping data, and so we have the original cross sections. And fortunately, there was another set of cross sections that were taken in '75. There is kind of a tragic dark period for data in this region, but we were able to calibrate the dam, and this is the calibration that you'll do to look at not only how much sediment deposited. That's actually kind of trivial to compute how much sediment deposited in this dam because it has almost 100% trap efficiency, so it's just however much it was delivered. But where it deposited, because that's going to matter if we try to flush this dam, we try to get sediment through this dam. What sizes and where ends up mattering a lot. And so this is our calibration. This is the calibration we're going to work on. And this isn't cumulative. This is just the volume change at each cross section. Why is there a big peak? Why did these get bigger as you go downstream?
Inflow location.
No, it's a change in the grade of the.
That's the upstream mouth of it.
That's right. There's a change in the grade. So think about our dam again, and we've got we've got the grade here, but we've got this backwater, which means that at this cross section, the maximum sediment you can have is like that. But at this cross section, the maximum sediment you can have is a lot more. And so that means that at this cross section, in about 15 years, you're going to have even more. Like this point is going to go up and off the chart because each successive cross section, the reservoir gets deeper and you can dump a bunch more sediment there. But this is a progressing delta, and you can see how the delta is moving and hitting each of these points. All right, but a lot of the work that John and I have been doing are 50 years later, 100 years later. These dams get built, they start to fill with sediment, and then they become liabilities. And the main thing we do with a dam that's full of sediment and has become a liability is we take it out, and we'll talk about that in a little bit. But a lot of times this infrastructure is really important, and we can't take it out, and there isn't like there's another place we can put this dam to replace whatever this resource was. And so one of the things that we're talking a lot about as our infrastructure starts aging is, well, can we manage these systems somehow to pass this historic sediment load, right? Like, it's not like the sediment is bad for the river. This is the historic sediment load of the river. And John's done quite a bit of work looking at, well, actually, when we put these dams in, we change the ecosystem downstream. Like there's a lot of river species that are actually, they're adapted to muddy water. It helps them hide. And so when you put the dam in and you get a nice clear water trout fishery downstream, that actually extirpates the natives because the natives need muddy water to hide. They're not fast. And there's a lot of things like that. And so one of the cases, this isn't a dam that filled with sediment, but this is a dam that had to start flushing periodically. And whenever you flush a reservoir, you're going to put a big sediment pulse downstream very quickly. And so you have to analyze the effects. There's a water treatment plant downstream of Fall Creek, and this is the only core reservoir that does a full drawdown flush every year. There's several reservoirs in John's district that do short flushes to clear out the sediment around their gates, but this is a full multi-week drawdown. And the reason they do this at Fall Creek is they have salmon that come upstream, which salmon coming upstream around dams is always obviously a challenge. But salmon coming downstream through dams is also a challenge because fish have what's called a swim bladder. One of the things that the Portland district has started doing, and in close conjunction with USGS and the Fish and Wildlife, is when the fish start going downstream, they draw down the reservoir so that the fish can go downstream without this big pressure gradient. But by drawing down the reservoir, they're also sending the sediment pulse downstream, and there are downstream interests. It could induce flood risk downstream. Once it hits the water treatment plant, it can overwhelm the water treatment plant. There are a lot of downstream consequences, and so we got to use this. RSM supported us to use this to kind of look at, well, what would happen if we tried to use RAS to do that? And so this is actually the reservoir. They draw down this reservoir long enough that they start to recruit some vegetation, and then as you're moving downstream, this is what it looks like during the flush. I have there's a cool video of this too that we could show at some point. But this is the 1D sediment model, and we're just going to look at what the sediment pulse does downstream. And so here we've got the diamonds are the USGS collects concentrations downstream. Another reason that I kind of want to walk through these stories is so you can see kind of the different ways we try to evaluate the model. We didn't have repeated cross sections here, but we did have downstream concentrations, and so that's what we used to evaluate the model with. And so the USGS collected these diamonds, which are downstream concentrations, and the brown lines are the concentrations that we got out of RAS. And so now we can use the model to look at, well, what if we changed the rate of drawdown? Or what if we held the drawdown longer or made it shorter? How does that affect our impacts downstream? Depending on the year, the Corps spends between 25 and 40% of its budget dredging. Most of that is just straight up fuel. Like in some ways, the Corps of Engineers is a fuel buying organization, and so anyone who can provide any efficiency to our dredging procedures. The other thing about dredging is I like to think of dredging. It's like healthcare and college. Like the rate at which the costs are increasing are much are nonlinear and much higher than inflation. And so we just got to do it better. Because no one's running for Congress saying, you know what we need to do? We need to dredge more, right? And so we just got to do better. We got to do more with less. That's just who we are. If you're not comfortable with that, you might need to find a different job. And so there are a couple kinds of dredging, as we've already alluded to. There's navigation dredging. I cut my teeth in the Great Lakes, and so these are the projects I'm familiar with. One is the first Sediment RAS model ever that was done by someone not at HEC, was done by Calvin Creech in the Detroit district on the Otonabee River. And they still use that model to determine whether or not they're going to dredge. Because it's a small recreational navigation port, and they don't actually have money to deploy multi-beam every year, so they use the sediment model and the inflowing hydrology from that year to determine whether or not they're going to have to dredge. And they still use it as an operational model. And then the model that you all are going to work on this today is the Cuyahoga River. The Cuyahoga River is kind of famous because it's the Clear Water Act. It's one of the most important events for the Clean Water Act, because the Cuyahoga River has caught on fire. So this is a disturbed system, but for those of you who are kind of from the Rust Belt or know the Rust Belt, it's a story of deindustrialization. And so this used to be a really active industrial channel. All the historic steel mills were along this channel, and they've all kind of either gone to urban decay or turned into dance clubs or coffee shops, the way that these Rust Belt cities go. But there still is some activity, as it would happen at the upstream end of this channel. And so the Buffalo District is thinking about, well, how can we maintain this channel for these dwindling customers, but we have to maintain the whole thing. Can we save on mob demob? Can we over dredge? Those sorts of questions are the ways that we can manage. And so we built this sediment model, the one that you're going to work on. And it looks like you're falling off a cliff, but again, things are exaggerated in the vertical. This is what navigation channels look like. We dig them deep until we don't. And so what you can see, and navigation projects are nice to work on because the dredgers have to get paid. And so in order to pay the dredgers, you take bathymetry before they start and bathymetry after they're done. And so you often have really nice calibration data, and then they do it again next year. And so if you want to look at how your system deposits, you take the bathymetry from after they're done and the bathymetry from before they start again, and that is a really nice 8-month snapshot of what your river's doing. And that's what we have here. These dots are the deposition that happened between dredges, and then this is my simulation, and this is the simulation you're going to do. These are the data that you're going to have to work with today. All right. We're also going to talk a lot about the Missouri River. We already have, but I have it in here for when John's not here. I probably should bring John up to talk about it. But the Missouri River, it's a different kind of dredging. In most cases, we have too much sediment, and we want to get rid of it, so we do the dredging. On the Missouri River, we call it channel mining. We don't have enough sediment, but people want it. And so we have to manage how much they can take. And so John's done a lot of work looking at the Missouri River. This is a 500-mile model. He built a 500-mile model of the lower Missouri. It's 800 kilometers, full mobile bed sediment transport model with multiple decade calibrations. And so what's going on is, because of this channel mining, the water surface elevation, not even just the bed elevation, the water surface elevation is dropping at Kansas City. And the bed elevation is changing. It has dropped up to 7 feet. And he talked about how that affects the infrastructure. And so this is the famous slide that John uses to get everything funded. If you want to think about how much sediment has been mined out of this channel, it's 49 times a football field times the Empire State Building. My daughter gave a presentation on the Rio Coca, and I took this slide and changed it for the Rio Coca, but didn't change it that much because it's a very similar mass. But it's a great way to kind of conceptualize how much sediment's moving, although it's not a great way to conceptualize outside of this country. And so whenever I give this talk internationally, I switch to SI units, which is 100 times a soccer pitch, a football pitch, times whatever the tallest building is in their city. This is Columbia. But you always have to switch to SI when you teach internationally. And so these are his calibrations. The really important thing about this is, John and I started working on this model before the 2011 flood. And we dialed this calibration in. It was very, very pretty. And then the 2011 flood happened, and we're like, oh, let's apply it to that. And it wasn't great. And so we actually had to revisit the model. And we'll talk about this in calibration. This is why multiple times series calibration, or what you might call calibration validation, is really important, is because your model has to be robust to all the conditions it'll face. And so these are the calibrations to this kind of low flow period that we originally calibrated to, and the period that includes the 2011 event, which we've already kind of talked about in the Missouri. The big events scour a lot and then rebound a little. I feel like this is a good picture of kind of the edge of what you can do with 1D sediment transport. It's a 500 kilometer regional model with that kind of calibration. I think this is probably the premier application of 1D sediment transport. All right, then finally, the reason I got an ecology degree was because I found that about half of my work had some sort of restoration tie-in. It wasn't half the funding, but it was about half the work. We have a lot of little restoration projects. They tend to be small. Some of them are, obviously, the Missouri River and the pallid sturgeon. And so one example, and we kind of alluded to this, this is Curtis Miller at the Omaha district. This is the Yellowstone River, and they have this irrigation channel where they kind of put up an inflatable dam and they send water to irrigators. But sturgeon in this part of the world and the ESA are kind of king. And so if you can do something for the sturgeon, you have to. And so the sturgeon should be able to get upstream of this important irrigation diversion. And so the Omaha district planned a sturgeon highway. Although, if you know anything about sturgeon, the highway's not very fast because this is an ancient fish, and you can't hurry a sturgeon. They will not be hurried. It's like Grandma in the fast lane. And so you'll notice that this channel is actually longer because you have to keep the velocities down. But what happens at diversions? Well, at diversions, if I take flow out here, I'm also going to take sediment. But I'm probably taking sediment from the upper portion of the water column, which means I'm not taking most of the channel forming sediment. I'm just taking kind of wash load and fine suspended load, which means I'm keeping most of the flow, and I'm keeping some of the flow, but almost all of the sediment. So a lot of times we get deposition downstream of the diversion. This is in the main channel. And then we come down here, and when the water comes back in, it comes back in clean. And so now we've got more flow, but less sediment, and so we tend to erode downstream of the diversion. But that's in the main channel. What happens in the diversion itself? Well, if it's totally novel earth, if you're just kind of carving a channel out of nothing, well, you're putting water in there and maybe some fine sediment, but no channel forming sediment. So what is the risk to this channel? Erosion. And so that's what Curtis Miller applied RAS. You can see some of his alternatives here, and you can see that the channel's gonna erode. It's gonna erode. But how much is it gonna erode? That's the question. And so one of the things that they did in their design is they said, okay, we're gonna excavate this channel, but we're gonna actually sieve the material, and we're going to keep the coarse material, and we're gonna replace the coarse material to kind of pre-armor it, to develop an armor layer, so that you're not just putting water into bare earth, but you're actually simulating what the river would have done as it cut down, accumulating the coarse material on the top.
So, has anybody ever looked at, not taking the water off the top?
Yeah, so that's the thing that Curtis did. Curtis's work here is really cool because we're going to talk a little bit about suspended sediment samples, and a lot of times those are depth integrated samples. So you put the sampler down and you bring it up and you get one integrated sample. They went out and did sampling and looked at what the actual concentrations were at different elevations, so they could think about how deep should we go with this water. And I talked a little bit about the Boulay effect, which I've been mispronouncing for years. But the interesting thing is that if you get this low enough so that you actually get bed load going into it, you actually get a disproportionate amount of bed load. That's the Boulay effect, is that you could actually have 30% of, if this is at grade, so you've got bed load, this is completely counterintuitive. I actually don't expect you to believe me, but it happens. It's why it's got a name. Is that if this is at grade, and you've got 30% of the flow going out here, what percentage of the sediment do you think you're gonna get? What percentage of the bed sediment do you think you're gonna get? 30 is a great opening offer.
Higher.
No.
Higher.
Is it like
80.
Why?
I know, right? And so Marcelo Garcia has like the seminal review paper on the Boulez effect, and I did a podcast with him, and we talked about this. It's not like central to his life work, but this blows my mind. You end up standing up helical currents here, and the helical currents go in this direction, and they sweep the bed load into it. But that's only for the bed load. The wash load and high suspended load is more of a 50-50 split. Now there's another nonlinearity that gets into account that happens there, which we'll talk about later today. But you do need to account for the Boulez effect whenever you're designing a diversion. One of the interesting things about 2D modeling is that 2D modeling will help you answer a lot of questions, but there are a surprising number of questions where 2D modeling is just as inept as 1D modeling, and something like that a 2D model would never capture. A 2D model will give you the exact same wrong answer as 1D, although they'll give you a prettier picture. And it's not always 80%, but the nice thing about Marcelo Garcia's paper is he did a review of all of these experiments, and some of the earliest ones, the second, Boulez is named for the earliest experiments, but the second round of these was actually done at ERDIC. The 800-pound gorilla in the room in restoration and sediment is dam removal. And here's the secret that you don't know. Well, you might know, but you might actually suspect. Why do we remove dams? 80% of dams are removed because of fish. No. Liability. That's right. If someone's going to pay to take out a dam, American rivers, they do great work, but they don't have the kind of money you need to take out a lot of dams. The thing that motivates most dam removals is we have this thing that no longer provides any value, that's full of sediment, and it's old. And if it was to break, people would die. And our company, our power company, owns this thing, and we need to get it off our books. And so they go to a local NGO or the Corps, and we tell a fish passage story, which is true. And we get a coalition of NGOs and public sector and private sector to bring some money together to get this thing out of there, because we all want it. But it's generally motivated by the dam owner who said, this is an enormous life and safety liability on our books. We've got to get this off our books. And so if you're interested in dam removal, that's the way it happens. And so this is Springville Dam in Buffalo District. All this work was done after I left the Buffalo District, but when you leave a district and go to a center, the district rightfully recognizes that they have some claim on your time because they developed you and sent you to HEC all those times. And so I supported a number of engineers as they worked on this. And this work was done by Waleska Echeria, who is Waleska Doyle now, and she works at ERDIC. She also went to the labs. But she built a sediment model of this dam removal. And so one of the interesting things about dam removal is that, Chris and I talked about this in the last podcast, is that I think it's harder than other models because you can't calibrate it. You're trying to simulate a completely novel event that's never happened in the past. And so you can't calibrate it. And so what Waleska did is she built this dam removal, and then she looked at different dam removal strategies. In dam removal, you've got the blow and go. You just say, we're going to dynamite this thing and just let it go. Or you can do stage removal if it's concrete. You can And so we did that, but then we also did sensitivity analysis on all this, because we said, we can't tell you an answer because we can't calibrate this model. But we can tell you, is it going to be days, months, or years? And that's the level of fidelity we can give you. And so then we did sensitivity analysis to look at, what is the time scale of the downstream effects? Is it days, months, or years? And there's a flood risk management channel downstream. There's walleye habitat downstream. And so we're like, yeah, the flood pulse will arrive in days. It'll last months, not years. That's the kind of storytelling and quasi-qualitative work you can do with a uncalibrated sediment model. The big sediment model, the big dam removal model that I did with Chris Nygaard that we talked about in this podcast was the Snake River. There are 4 dams on the Snake, and they've been there since the 70s. And so when we had to do a new EIS for this whole Northwest system, they got public comments that we should evaluate dam removal as an alternative. And so they turned to Chris, and he called me, and we did this dam removal. And we did the same thing here because in this alternative, 2 of the dams come out. The upstream dams come out one year, the downstream dams come out the next year. But the sediment flows downstream into the backwater of another reservoir, and that deposition could cause flood risk for those communities. Plus, anytime you do a dam removal, you're trying to do it ostensibly for the critters, but like fish don't love huge sediment pulses. And so you also have to evaluate what are the peak concentrations you're going to get, and what's that going to do to your biological communities. And so the first thing we did is this will become a theme. I'm going to say this a bunch of times. I want you to hear it now. The first thing we did is we calibrated the hydraulic model. You cannot build a sediment model with an uncalibrated hydraulic model. Errors propagate the more things you add. And so we calibrated the hydraulic model. The second thing we did is we built a sediment budget. There's a reason we just spent 2 days talking about this, is because you want to build a sediment budget before you build your model. If you don't do these 2 things, your sediment model will not calibrate. Or if it does, it will calibrate for the wrong reasons and it won't predict. And we'll talk about all of that stuff. And so we had bed gradation for each of the dams. This is a way that I like to visualize bed gradation and bed gradation trends. Black is percentage of silt. And you can actually get these plots in RAS now. You guys will get a chance to look at, you can plot RAS results with, I think this is called the waterfall plot. And so you can see that, as you move farther, closer to the dam, you get less sand and more silt and clay. And that's what you're looking at here. And the same pattern repeats for all of the dams. And then we calibrated deposition. We also calibrated drawdown. This is what makes this dam removal study special, is because usually you can't calibrate a dam removal. But in 1992, they drew down the reservoir. And if you draw down a reservoir enough, you mobilize the sediment in the delta, you essentially simulate a dam removal. And so we had bed change and concentration from this drawdown. We could actually calibrate our dam removal. And so we did. And so they got 6 to 10 feet of cross-section change in a 10-day, 30-foot drawdown. That's something you can calibrate to, and we did. And then we simulated the future. And you can see the concentration, we got peak concentrations based on the removal. The moral of the story is you're looking at peak concentrations around 25 to 30 parts per million, which is bad but not terrible. And then those peak concentrations are done after the second year. And you move to much smaller concentrations and mainly bed load moving through the system. I guess let me just do this last one. Another big ecological impact of sediment is reef blanching. Reefs are symbiotic organisms, and they're photosynthetic, which is awesome. It makes them super magical, but it also means that if you decrease the light penetration, you can kill them. And so a lot of reefs, including the ones in Hawaii, we've been working with Honolulu District on this, and obviously the most famous reef in the world, the Barrier Reef. All the agriculture that's going on in the coastal watersheds is delivering a lot of sediment to the reefs, and it's obviously warming and increased oxygen, increased carbon in the water is a really big deal for the reefs. That's one failure mode. But the more critical failure mode is that the number of days of appropriate light penetration that these reefs are getting is just not enough for photosynthetic organisms, and they're dying. And so a lot of folks are looking at is there a way to deliver less sediment. And this is one of the sneaky sediment modes that people don't recognize, is that if you have a watershed leading to a reef, where does the sediment come from? So like, there's a farmer's field here, there's a construction project here,
Everywhere.
All throughout.
right? What percentage of the sediment comes from these like distributed watershed sources?
Depends.
Depends. What do you mean?
Depends,
High or low?
It will
Probably
be
in a high agriculture.
agriculture means high.
Generally, I think high.
Yeah.
But there's been a lot of work done by HEC-RAS down in Oxford. HEC-RAS is one of the labs with the USDA. Our friend Eddie Lincoln down there, Andrew Simon, have demonstrated that more often than you would think, these loads, these sources are on the order of 50% or less. So where's the rest of the sediment coming from? It's from bank erosion. And so you have these channels, and yeah, the channels erode a little bit vertically, but what's really happening is you're not only putting more sediment in there, you're putting more flow, right? Because you're getting rid of all the trees. And the banks are eroding. And this is why sediment budgets are so important, because more than 50% of the sediment that's going through the reef is bank erosion. It's not distributed source from agriculture. It is from the agriculture, but it's from the flows of the agriculture. And one of the things that Jim Selgin at the Detroit District can do is he goes and he looks at the material that's been dredged, and he does soil fingerprinting. And so he can tell what percentage of the soil comes from the farmer's field or from the banks. Again, it's like witchcraft. He's like a wizard. I've never involved him in a project, but if you're interested in that like it's really interesting. And so, we talked about how RAS changes the cross-section vertically, right? But for this project, this is where we added the USDA's B-stem model. And the ARS has a test watershed called Goodwin Creek, and they've measured channel bank widening on this creek for 30 years. And so it's kind of the test watershed to test these kinds of tools. And I think they've got something like 47 repeat cross sections or something like that, which is a really beautiful data set of a pretty dynamic widening project. And so we have a widening model in RAS. You're not going to use it unless you really, really need to, because it's very data hungry and honestly it's quirky. But if you do need this kind of bank widening capability, we do have it in RAS, and this is our model of Goodwin Creek. The dotted lines are the observed bank migration, and the solid lines are the computed. And this isn't calibrated. I didn't change my knobs until I got this right. I used their parameters, the parameters that ARS has always used for their model, and I just put them in RAS to see how RAS would do. And so this is kind of a model validation. And so we can do bank migration. It does, again, we're already adding a degree of freedom. You used to just change the water surface. Now you change the water surface in the bed, and it's gotten 100% harder. Now you're going to change the water surface, the bed. Oh, I didn't mention that. Welcome to varsity modeling. And then you change the water surface in the bed and the bank, and now you're playing in the NFL. And it's yeah.
Doesn't the bank change in the RAS sediment modeling?
So in the RAS sediment model,
Like in the cross section, do you change?
we'll talk more about this later in the day or maybe tomorrow. By default, when RAS updates the cross section, we only raise or lower the wet nodes. That's all we do. And so if you've got water in your overbanks, we'll raise or lower those nodes, but we don't move them laterally unless you turn on the B-stem model. And then the B-stem model will move anything outside of the banks laterally. And so then you've got these nodes moving up and down, and these nodes moving sideways, and you can get some funny shapes. It starts looking very Picasso-y very quickly. That's an adjective I've never used. We'll come back and talk sediment processes, and we'll kind of see where we are from there.